Hello all, my name is Dimitrios Tanoglidis and I'm a PhD student at the University of Chicago. Today I'm going to present how to use deep learning to find low surface brightness galaxies and separate them from many artifacts that we have in astronomical images. Let's start by the definition of low surface brightness galaxies. These are diffuse galaxies with a surface brightness that is at least 1 magnitude less than the ambient sky. So in magnitude, that means more than 24 magnitudes per square arc seconds. And low surface brightness galaxies, because of their actual nature, are difficult to detect because they're very faint. And for that reason, it's also very difficult to study them over a wide sky area and in different environments, such as galaxy clusters versus the field. So we would like to have many of them and discover many of them to test models of galaxy formation, uh, what we call the galaxy halo connection. So how galaxies are being formed inside dark matter halos in a regime that we do not have many observations. And also recently there was a renewed interest in a special class of low surface brightness galaxies called ultra diffuse galaxies that are basically very large low surface brightness galaxies that kind of do not agree with galaxy formation models. Um, so we are going to use data from the dark energy survey. So let me briefly describe it. It is an optical and near infrared survey on the 4-meter Blanco telescope in Chile. Covers 5,000 square degrees on the sky on 5 photometric bands, which means that we don't have a redshift or equivalently distance information. And it ran over a little bit more than 5 years, close to 6 years, with the last observations taken on January of 2019. And over these 6 years, it measured the properties of more than 300 million objects. And you can see like stars, galaxies, etc. And you can see the footprint of the dark energy survey known as the tank on the southern part of the sky. So that's the survey, the data that we are going to use from this survey. I'm going to present you a catalog of low surface brightness galaxies from the first 3 years of observations, so the data from the first 3 years that we recently discovered and analyzed. And by showing you the 3 main steps, I will present first of all the challenges that are associated with discovering low surface brightness galaxies that will motivate the need for using deep learning. But also I will present the sample that I'm going to use as a training set for training deep learning models. So we started by performing some selection cuts on the total DS catalog of the 300 million objects. And the 2 most important cuts criteria were on the mean surface brightness. So we selected faint objects. And also we restricted ourselves to objects that had angular sizes on the sky larger than 2.5 arc seconds in order to remove contamination from very small objects. And of course, some other criteria to also narrow down our selection. And we had a little bit more than 400,000 candidates, but this does not mean that all of them were actually low surface brightness galaxies. And actually, this is the problem that motivates the need that we have to do something, use machine learning or deep learning, because many of them, most of them, more than 90% of these candidates are artifacts, as we can see here. Some that are very close to stars, like some diffuse light around the halo of galaxies, diffraction, etc., that is being blended and confuses the system as low surface brightness, as real low surface brightness objects. And of course, we cannot inspect 500,000 images. So the second step we took for that catalog, to create that catalog, was to use a machine learning classifier. Of course, the problem was that we didn't have labeled data. So in order to do that, in order to get some labeled data, we inspected some regions on the sky, smaller regions like 4 by 4 square degrees, and inspected all the objects that were passing the previous criteria. So we created a training set that had almost 8,000 objects, and out of them, almost 700 were low surface brightness galaxies. And we selected a classifier that was minimizing the false negative rate, so we didn't want to miss any galaxies, but we were thinking that we can afterwards inspect all of those that were classified as positive by our classifier. So the best results were by a support vector machine classifier using features as the size, the radii of the objects, the mean surface brightnesses, the astronomical colors, the ellipticity, etc. And the sample, of course, like the test sample, is highly imbalanced. It reached a completeness, also known as precision in the machine learning literature, of 90%. So in other words, missing like 10% of the total number of galaxies, and a purity of the sample, also known as recall, or 56%, which means that we have many in those classified as positives that are not actually low surface brightness galaxies. And that motivated us, that required us to go through a third step of visual inspection. So we checked all those that were past the classifier, and we found, like as you see here, those that are real galaxies and the remaining astronomical artifacts, imaging artifacts. So by doing that, of course, we had the catalog for analysis and study low surface brightness galaxies. But the bonus from having from doing this exercise was that we had a very large annotated data set, so positives and negatives. Imagine, I remember that we started from 40,000 candidates here, and we went down to 20,000, 21,000 galaxies. So we have now approximately 20,000 low surface brightness galaxies and 20,000 artifacts that we can use to train a deep learning model that we generally know that when you have imaging data and a large number of them can tend to overperform other machine learning techniques. So beyond wanting to do this exercise for low surface brightness galaxies in DES, we know that in the future, if we want to push the low surface brightness science, we may need to use such automated techniques because the data will be really big. For example, the upcoming legacy survey for space and time on the Vera Rubin Observatory that is expected to start very soon, it will measure an area on the sky of almost 20,000 square degrees. And we are going to get 20 terabytes of data per night and have a catalog of 20 billion galaxies after 10 years of observations. So we are talking about really big data. And in this case, any thought about visual inspection will be just impossible. So we have to start using deep learning techniques if we want to analyze such data. So here I'm going to present the main result of this paper, the main part of this paper, the main part of this work, which is using a convolutional neural network to classify low surface brightness galaxies and artifacts. So at the image level. So we are going to use a simple architecture for the convolutional neural network, consisted of 3 convolutional followed by pooling layers with dropout, and then followed by 3 dense layers. We tested more complicated architectures, but we found that this performs like this has the optimal performance in terms of accuracy of classification. The thing is that to use convolutional neural networks, that requires a large number of label training instances, examples, but the good thing is we just created one, as I showed you earlier. So these are some examples of low surface brightness galaxies and artifacts that we are going to use for our selection. For our training, we randomly selected 20,000 low surface brightness galaxies and 20,000 artifacts, and we split them into training, validation, and test sets, as you can see here. And let me show you a little bit the first result. So this is like the accuracy and loss as a function of an epoch. You can see both the training and validation, and we applied some regularization techniques to avoid overfitting, and you can see that the two curves agree quite well. So we do not have overfitting. And here I show the false positive and true versus true positive rates, the usual ROC curve, to compare the classification from the convolutional neural network, but also the classification from other machine learning techniques, such as support vector machines and random forests trained on the same data. When I say the same data, I mean the same galaxies, but using features such as radius, surface brightness, as we had done in the original catalog, but using a much larger data set now. And as you can see, even visually, the convolutional neural network tends to significantly overperform the other techniques. Some more results. You can see the confusion matrix, the true versus predicted labels for the test data set. We achieve an accuracy in the prediction of 90%. With a precision of 90%, so we miss less than 10%, something like 9.8% of the low surface brightness galaxies that do not pass our classifier. And probably a very, very significant figure is the recall or the purity of the classifications, which means from those that are classified as low surface brightness galaxies, how many are actually low surface brightness galaxies, and this is more than 92%. And you can see some of the misclassified objects. The interesting thing is that actually some of them may be a real low surface brightness galaxies that we mislabeled, or actually we were too conservative when we were selecting our data set, and in some cases that we're not 100% sure, we included that as artifact while it was not. So these metrics can be actually even higher if we do a more careful labeling. So let's check also, we tested the robustness on splitting the data set in different ways. So you can see that even if we change the split using different random seeds in the separation between training, test, and validation sets, the results they stay pretty much the same. We don't have much variation. Okay, now the real deal, I think, because okay, we showed the results on the dark energy survey, but apparently, but we will have to use this classifier and probably something trained on DES to find low surface brightness galaxies from another survey in the future. And to test if we have hopes for this to be possible, we used data from the Hyper Supreme camera that they had released a catalog of almost 800 low surface brightness galaxies. And we also asked from the authors to give us some of their false positives that were not released, but we really thank them for allowing us to use them. So we had a sample of 640 low surface brightness galaxies and 640 artifacts. And we did two things. So first, train on DS data, as I showed you, and apply directly to hypersupreme camera data. And in the second case, retrain on a small hypersupreme camera sample with very low learning rate on top of the training that happened like from the DS data. So we separated this sample into 320 examples for the retraining part and 964 testing in both cases. And you can see again from the false positive rate through positive rate curve that the performance after fine-tuning is significantly improved. Although both are very good, both reach an area under the curve more than 90. Fine-tuning helps to significantly improve the results when we transfer our learning from the DS data and want to classify galaxies from a different survey with different specifications. Let's see the confusion matrices for the two cases and the accuracies. We see like we go from 77% to 87%. Of course, it's not as accurate as the results from the DS survey itself, because different specifications from the survey, but probably also different human biases when labeling objects in the two surveys, like being labeled by different people. So improvement in accuracy, also in recall, and in precision, very significant improvement in precision. Let's see again some misclassifications. So these are some artifacts classified as low surface brightness galaxies. Some of them probably they are. These were probably very bright galaxies that they didn't want to include, but nevertheless are galaxies. And some low surface brightness galaxies that were classified as artifacts. These seem to be the faintest objects out there. So these were the results. They were really promising, and I hope that in the future we will be able to use deep learning to find very large catalogs of these objects that are extremely interesting and will help us to better understand the process of galaxy formation. And I would like to thank all my collaborators, my advisor, Alex Wagner at the University of Chicago, that helped me to make this possible. Thank you very much.